happy that you're here with me, and I apologize. This was supposed to be uploaded significantly sooner, and I appreciate your patience. Um, let's jump right into it. Number one, we have we got a sealed rigid container holds an equilibrium mixture of the system represented above, um, delta H being greater than 0. Automatically, I know that that means that this is going to be endothermic right off the bat. That's the first hint that they gave me here. A sealed rigid container, which of the following changes will decrease the amount of I2? Okay, so I2 is on the right side. It's a product. Okay, so decreasing the volume of the container is going to cause an increase in pressure. Okay, so for letter A, if we increase the pressure, and let me hop back over to let's go to it should be posted right here in the lecture. Le Chatlier shortcut is what I'm calling it, and this is what you guys want to use. Like this, of the materials I've looked for, this is my favorite. That kind of summarizes and helps you wrap your head around this concept. Pressure. As pressure increases, it favors the side with fewer molecules. Okay, so let's hop back over there. So the side with fewer molecules. Which of the following changes will decrease the amount of I2? Okay, fewer molecules. On this side, we have a total of 2 molecules. Okay, and on this side, we have 1, 2. Over here, we have 2 molecules. So is it going to matter either way? No, it's not going to. So I'm going to be extra and just cross that one out and say nope. Increasing the temperature of the system. If I increase the temperature of the system, I'm going to go back and cheat. Increase favors an endothermic reaction. Okay. So if we head back this direction, okay, if this is endothermic, that's going to favor to the right. That's going to favor and cause more of the product to be made. Okay, but we're trying to decrease the product. So that's not going to work for us either. If we add some HI at a constant temperature, we know that that's going to cause the reaction to shift towards the other side to help balance it out, which also means there'll be more of that iodine made. Adding some more H2 at a constant temperature. So if we add a little bit more of this H2, okay, we're adding more of the products, and it's kind of to think of it as like a balance or as a scale. If you add more of the products in an equilibrium, you're going to shift to the reactants, causing there to be less of whatever was left behind. So D would be my best bet for number 1. That's it, team. That's what we needed. That's what we found, and that's what we needed. Okay. All right. For some reason, I don't know what's going on here with this guy, but we're just going to rock and roll. Sorry for any distraction there. Okay. Let's head over to number 2. Okay, we've got an iron and then this cyanide compound, sulfur cyanide ion. I'm sure this has a different name. And then we have this iron, and then it's also an ion as well. So we have 2 molecules, okay, becoming 1. So if we can see that, we've got 2 ions, okay, on this side becoming 1 ion. Okay, and then we've got delta H is less than 0. That is a fancy way of saying that something is exothermic in this case. Okay, so if it's exothermic, the solutions of Fe and are mixed and allowed to equilibrium that there, which the following best predicts what will happen if we raise the temperature. Okay, let's look at our cheat sheet. Okay, if we raise the temperature, it favors an endothermic reaction, which we just established this is an exothermic reaction. Okay, so it's going to do the opposite. It's not going to go forward like the exothermic direction from left to right. It's going to go backwards. Okay, because it favors an endothermic, which is the reverse. So if we're going to go in the reverse, it's going to be more colorless or more clear. Okay, the reaction becomes less red, more red, more red. Okay, so it's either going to be A or B, because we know it's going to shift to the left. Wow, my mouse lines are pretty rough here. There we go. That's A or B. And we need to now think about our equilibrium constant. Is it going to decrease or is it going to increase? Okay, so as it shifts, okay, to the left, there's going to make more reactants. Okay, and if I were to type in, okay, reminding us what our K is equal to. Our K is equal to products divided by reactants. Okay, so therefore, if our products over reactants started at 1.2, then if the reactants increase, we then would get 1 over 3. Okay, or maybe then it could become 1 over 4. Okay, so notice as those reactants increase, what is happening to our K value? Okay, the K value is going down. Therefore, my answer is A, right there. Okay, let's keep rocking and rolling. We're at 7 minutes here. Let's see what we can get done. Okay, on number 3, after the system above reaches equilibrium, additional OT is injected into the flask at time t while the temperature is held constant. Which of the following graphs best shows the rates of the forward and reverse reactions as a function of time? Okay, so if we were to put a whole bunch more here, okay, and that's what they tell us they're going to do, it's going to be a huge jump in the forward direction. They're just going to wham, we're going to make a whole bunch of that all at once. So we need this solid line. It's going to be a huge jump. Oh boy, power's getting low here. Huge jump forward. Okay, let me pause this. All right, team, so if we add a whole bunch more of the oxygen, that forward reaction needs to jump. So I've got an A value that jumps, a forward that jumps right there. So it could be A. This one, the reaction rate goes way down at that point at time 1. And this one is just this nice little curve. No, it's going to be a huge jump if we add a bunch of oxygen. So it could be D as well. So it's going to be A or D. Okay, and then the difference is the reverse reaction. So with A, our reverse reaction is at this one value, and then it slumps, and then it flattens out. But what's interesting, if we add more of any concentration to an equilibrium, okay, we have this very equilibrium state, and then wham, we make a change. Okay, not only is it going to change in the forward reaction and increase, any more concentration is also going to cause the reverse reaction to increase. So that is why D is the correct answer. A shows that the reverse reaction would go down, and that's not true, because if we make more products, then in an equilibrium, we're also going to make more reactants, which is why the answer is D. Okay, and I maybe really quickly, okay, if we make more products, then we will also make more reactants. Okay, let's see if we can, right there. And that's why the answer is D there. Okay, for which of the equilibrium systems represented below will reducing the volume of the reaction vessel at constant temperature cause more products to form? Okay, so we're going to be reducing the volume. Okay, reduced volume is the same as increasing pressure. Okay. And so if we reduce the volume, we're increasing the pressure. Let's go back to our cheat. Okay, our cheat tells us that if we increase pressure, it's going to favor the side with fewer molecules. Let's head back over here and take a look really quick. We've got here, we have 2 molecules. And right here, we've got 3 molecules. Okay, right here, we have 1 molecule. And on this side, we have a total of 2 molecules for B. For C, it looks like we've got 4 molecules on the left. And for C, we have 3 molecules on the right there. This guy, we've got 2 and 2. For which of the equilibrium systems will reducing the volume cause more products to form? Okay, so we want more products to form. Okay, reduce volume, increased pressure, and my cheat sheet told me favors the sides with fewer molecules, which is we're looking for more products. Okay, so A, did we favor the products? No, because increased pressure favors the side with fewer molecules. Nope, doesn't work for B either. Okay, because because the increased pressure favors the reaction, or favors the side with fewer molecules. Right here we have the same for D, and the answer is definitely going to be C there for us. And that's the reason why is because we have 4 on the left side and 3 on the right, and increased pressure favors the side with fewer molecules. And C is the only one where there's fewer molecules on the product side. All of the rest, they're either even or there's fewer molecules on the reactant side. All right, team, not my best video, not my best teaching, but I hope that this helps you guys to be able to wrap your heads around any of these problems if you struggled.